Hello all, welcome to the Autotronics course. So in the last class we had a detailed discussion about the intermittent fault, about the different categories of the root cause in detail, and we also had some discussion about the diagnostics of this intermittent fault, then the challenges in diagnosing an intermittent fault, and then we also had a discussion about the different approaches which are available in the intermittent fault, especially on data driven diagnostic method, about the detailed characteristics, etc. Now in the last class we touched upon the architecture of an intermittent fault diagnostic system. So as we had discussed earlier, an intermittent fault diagnostic system in Autotronics detects, records and analyzes the transitory and unpredictable defects that causes intermittent disruption to vehicle electronics or sensor systems. Such a system architecture combines specialized hardware for high-speed parallel signal monitoring with sophisticated software for real-time analysis, fault isolation and communication integration across the vehicle network. Now under this we have the front-end signal acquisition and condition, we have the high-speed data acquisition hardware, we have the digital signal processing and feature extraction, we have a fault isolation and diagnostics logic, integration with vehicle communication systems, then we have a user interface and a data visualization, and a system level features and design considerations. Now let us discuss about the front end signal acquisition and conditioning, where like we have the high sensitivity analog front end. The main capability is it captures the raw sensor or system signal, often very weak and prone to noise. It includes amplification, filtering and isolation circuit to ensure a signal integrity. This stage prepares signal for accurate digitization and analysis. Similarly, when we look into the simultaneous multi-channel monitoring, we have a multiple sensor or ECU signal lines are monitored in parallel to capture the faults anywhere in the system instantaneously. It ensures that there is no critical transient event is missed due to the limited sampling or the single channel focus. Now let us discuss about the high speed data acquisition hardware, where there is a fast sampling rates is there, like there is a transient causing and a transient intermittent faults may be extremely short, microseconds to milliseconds in the order. These high frequency sampling enables comprehensive capture of such fleeting anomalies. The event triggered buffering and storage. So to manage a large data volumes, the system records only a data segment around the detected anomalies rather than the continuous logging. This selective approach optimizes memory use and reduce the post-processing complexities. Then we have the time stamped data, which is a kind of a accurate time stamping which allow correlation between faults and vehicles, operational states, starting from speed, load and temperature, and it also aids to the root cause analysis. Then we have a digital signal processing and a feature extraction, where we have a kind of a pre-processing, where we have a digitized signal which undergo filtering, normalization and noise removal to enhance the signal quality. We have the feature extraction algorithm. In the case of the feature extraction algorithm, we have the extractional key signal characteristics such as amplitude variations, frequency content, entropy metrics or transient spikes that indicate anomalies. Then we have a fault classification and pattern recognition, where there are certain machine learning models are there or statistical methods are there to analyze the feature patterns to classify and differentiate fault types and the severities. We have the fault localization. As far as fault localization is concerned, the algorithm attributes to fault to specific subsystems, sensors, wirings, segments or control modules based on the signal origin and the fault signature. Similarly, there is a kind of a diagnostic decision making systems are there. So these diagnostic decision making system, it combines evidence from multiple channels and diagnostics rules to determine whether a detected anomaly constitutes a genuine intermittent fault or a kind of a harmless transient system. Next, we have a kind of a prioritization and altering. So like when you have a kind of a multiple systems or the multiple decision systems are there you may need to prioritize based on the critical faults which are flagged immediately for operator or service. Technician attention, while less urgent anomalies may be logged for the trend analysis. Now let us discuss about the integration with vehicle communication system. So when we look into the integration with vehicle communication system, we have a connectivity to ECUs via CAN, LIN, FlexRay and the Ethernet. The diagnostic data is communicated in real time or periodic reports to central vehicle computers or telematic units. Then we have an onboard diagnostic interface which enables a kind of an external diagnostic tool to query logged intermittent fault data. It freezes the frame snapshots and event histories. Next, when we try to talk about the gateway logics, we have the kind of a coordinated data flow between the different electronic domains or zones to ensure the coherent system and the wide diagnostic informations. If we consider the user interface and the data visualization, so we have the dashboard indicators which gives a kind of an immediate warning for detected faults and it ensures a driver awareness and the safety. With reference to a diagnostic software tool perspective point of view, the technician uses a kind of a detailed log with detailed logs either in the form of a kind of a sheet or it might be in the form of a waveform visualization, and in certain case it might be a kind of a fault reports during service for efficient troubleshooting. Then we have the kind of a remote monitoring and predictive maintenance which includes a telematic integration enables off-site analysis and early fault detection to prevent the breakdowns. Next, we have the system level features and the design considerations. So one of the system level features and design consideration includes the robustness and the fault tolerance. The architecture is designed to operate continuously without interfering with the vehicle functions with fail-safe mode to avoid the false alert. This is highly unique system which is being developed. Next is with reference to scalability perspective point of view, the modular design allows adding monitoring channels and upgrading algorithms as vehicle complexity increases. Then we have a kind of a real-time operation which is essential for safety critical systems, enabling an immediate detection and mitigation of the kind of an intermittent faults. So let us discuss about the intelligent collaborative diagnostics. So if you look into the intelligent collaborative diagnostics, so an intelligent collaborative diagnostic system for Autotronics is a revolutionary technique that combines the artificial intelligence, machine learning, cloud computing and real-time communication technologies to build a full vehicle health management ecosystem. So unlike the traditional reactive diagnostic procedure, this system provides proactive, predictive and collaborative monitoring of automotive electronic system throughout the vehicle cycle. So if you look into the vehicle cycle, we have the automobile to the vehicle sensor to the onboard diagnostics unit, onboard diagnostic unit to the cloud computing, then we have the technical expert to the OMA database and the report. This OMA database gives the information to the diagnostic algorithm and the report gives a feedback loop to the report and finally it goes back to the automobile characteristics. So some of the key characteristics of these system includes, one is a kind of an intelligent layer where the AI system can detect anomalies in sensor data with up to 95% accuracy, enabling the early issues identification. So you have a machine learning and a deep learning algorithm which can detect a small irregularity in the sensor outputs, leading to early problem detection that outperforms the traditional threshold alarms, consistently increasing the diagnostics accuracy with pattern recognition and predictive analytics. Now, if you look into the collaborative framework, there is a multi-stakeholder integration involving vehicle owners, technicians, OEMs, service centers, and cloud-based diagnostic platform. In addition to this, there is a kind of a real-time data sharing between the vehicles, repair facilities, manufacturers, and diagnostic specialists. Then we also have a kind of a remote expert assistant where the technician can collaborate with the specialized and AI system for a kind of a complex diagnostics. So we also have a kind of a fleet-wide knowledge sharing, enabling a kind of a collaborative learning from the diagnostic pattern across the multiple vehicles. So this is a kind of a collaborative framework, and then this is a kind of an intelligent layers which has a different systems. Then we have also have the real-time monitoring capabilities, the continuous health monitoring through telematic system that track the vehicle performance almost 24/7, and it also gives a kind of an instant fault detection and immediate notification to relevant stakeholders. So there is also a kind of a live data transmission via a cellular, Wi-Fi or a satellite network for immediate analysis. So there are different hierarchical layers of intelligent collaborative diagnostic systems are there. So the intelligent collaborative diagnostic system is based on the open systems interconnections, which we call it as OSI model, a conceptual framework that standardizes network communication into 7 hierarchical layers. So each layers performs specific functions, enabling the interoperability between the different systems and the technologies. So if you look into the different layers of this system, one is the diagnostic services, we have the data conversion, second we have the session establishment, third we have a transport management, fourth we have a network routing, fifth we have a data link, sixth is the physical connection. So what happens is, when you have an interoperability, they discuss among themselves to form a robust, intelligent, collaborative diagnostic systems. Now let us discuss about the different hierarchical layers of these collaborative system. The first physical layer one, which defines the physical connection via the diagnostic link connector, which we call it as DLC. So basically it includes pinouts, voltage levels, and signal characteristics. Some of the diagnostic standard includes SAE J1962, then we also have ISO 157654, ISO 91412, and SAE J1850. If you look into the data link layer 2, it handles message framing, error detection, and arbitration on the bus. Example CRC and CAN arbitration, where you have an ISO 157654 CAN, we have an SAE J1850 and ISO 91412. Third, we have a network layer 3 which route diagnostics message to the correct ECU using addressing schemes. So in this addressing schemes, we have a ISO 157654 and then SAE J1979. The fourth one is the kind of a transport layer 4, which manages the message segmentation and reassembly, flow control, and error recovery. In this particular process, we have a ISO 157652, which is a kind of a CAN transport layer, and SAE J1979. Next, we have a session layer 5, which establishes and maintains a kind of a diagnostic communication system sessions, which includes ISO 14229 and ISO 157654. The sixth layer is called as a presentation layer. The main function of this presentation layer is to convert the raw binary or hexadecimal data into a human readable or interpretable format, where we have the SAE J197 OBD2 PID decoding systems are there. And the last layer is the application layer, which defines the diagnostic service and data exchanges, example like retrieving DTC emission readiness. So we have SAE J1979, SAE J2012 DTCs and ISO 14229. Now let us discuss the core technologies which are directly like deployed for such kind of these autotronic systems. Like one, especially with reference to diagnostic perspective point of view. One is an AML, where the primary function is a kind of a pattern recognition and a predictive analysis. One of the key benefits includes the 95% fault detection accuracy and a 90% faster diagnostics. With reference to implementation perspective point of view, these engine defect decisions and brake wear prediction are considered to be one of the key aspects. Cloud computing perspective point of view, a remote processing with scalable storage, elastic resources and cross life cycle monitoring, and implementation perspective point of view, OTA updates and remote diagnostics. So we have a IoT connectivity, where there is a kind of a real-time communication and data transmission. V2S communication, continuous connectivity, where a 5G network DSRC protocols are deployed. Then we have a edge computing, where there is a local processing and the immediate response are observed. There is a reduced latency real-time decision and the onboard diagnostics fleet managements are established. So in addition to this, we have a big data analytics, where the sensor data processing trends analysis. Key benefits includes a kind of a fleet-wide insight usage optimization and a telematic analysis and a fuel efficiency. When we try to talk about digital twins, which are considered to be one of the key aspects in these like automotive system, especially with reference to diagnostics perspective point of view, we have the virtual modeling and simulation testing, accelerated development and predictive maintenance, and a will testing and a component simulations are established. Now let us discuss about the system workflow overview. So in the vehicle data acquisition, the sensor deployed across the vehicle. So as we had seen in the earlier slides also, and that is an actual aspects. The electronic control unit receives the sensor data, aggregate it, perform local check for anomalies and communicate within the vehicle through a network such as CAN bus or automotive Ethernets. So if you look into the overall flow, we have a deploy sensor, where sensors are placed throughout the vehicle to gather data. Then it collects the data, where sensors continuously collect performance and environmental data. Then it receives the data, where ECU receives the data from the sensor. Then we have an aggregate data, where ECU combines the received data for analysis. We have a performance check, where ECU check for the anomalies in the aggregated data. Finally, we have a communicate data, where ECU communicate data through a network like CAN bus Ethernet. When we try to talk about the telematic data concentration, all subsystem data flows through a telematic control unit, which we call it as a TCU. This serves as the central integration and a communication hub. So this telematic control unit pre-processes raw data and applies local analytics or early warning algorithm and ensures data security before the transmission. So if you closely observe in this, there is a data flow initiation, where data from various subsystems begins to flow. Then you have a TCU integration, where data is integrated into the telematics control unit. Then we have a pre-processing, where raw data is pre-processed by the TCU. Then we have an analytic application, where local analytics or early warning algorithms are applied. Then we have a kind of a security assurance, where the data security measures and implemented. Next system is called as a secure vehicle to cloud communication. So the TCU sends the diagnostics and operation data to the cloud servers securely using an encrypted transfer and standardized protocols like MQTT and HTTPS via 4G and 5G, Wi-Fi or satellite link. So in this particular process, we have a TCU pre-processed data. So the TCU prepares data for transmission. Then we have a data encryption where data is encrypted to ensure safety. Third, we have a data transmission where the encrypted data is sent to the cloud server. Fourth is the cloud server reception where cloud servers receive the data securely. And fifth is the data storage where data is stored in the cloud for analysis. Now, when you look into the cloud-based data aggregation or analysis, this cloud-based diagnostics platform receives a kind of a real-time stream from the entire vehicle fleets. So if you look into the AAML algorithms and analyze the anomalies, compare across vehicles and update predictive diagnostics models, there is a maintenance threshold, fault codes and systems health prediction are calculated centrally. First is it receives a real-time stream where the cloud platform receives the data stream from the vehicle. It compare across the vehicle, that is the data is compared across the vehicle fleet. Then it analyze the anomalies and the ALML algorithm analyze the data for the anomalies. We have a calculate maintenance threshold. The maintenance threshold are calculated centrally. Then there is an updated predictive model which predict the diagnostics model which are updated. Next, we have a predict system health where the system health predictions are made and the general fault codes where the fault codes are generated based on the analysis. Now, if you try to talk about the system workflow on an overview, so there are different collaborative stakeholders which assess and alter. So the technician receives an insight via a mobile app or dedicated workstations with prioritized alerts, faults, root cause analysis and recommended actions. So the OEM manufacturers can remotely monitor a vehicle health, deploy software firmware and updates OTA and refine future product design with anomalies fleet data. These fleet managers get fleet status, dashboards, predictive maintenance and recommendations and historical diagnostics logs. The driver operators receives an user-friendly alerts, dashboards, smartphones for critical maintenance of safety issues. So some of the vehicle data includes the technical receive, prioritize, alert and root cause analysis, OEM monitor health, deploy updates and refine design. Then we have the fleet manager access dashboard and maintenance recommendation. And the last is the driver which receives an alert from the maintenance and the safety related issues. So these are some of the vehicle data insight which will give us a clarity like how to implement this data and how to channelize this data for a efficient data analysis. Next is with reference to machine learning model refinement where a diagnostic results, repair outcomes and vehicle usage feedback continuously train and improve the central machine learning models. The system evolves to adapt to emerging patterns of failures and new vehicle technologies benefiting all stakeholders. So one includes a diagnostic result collection, that is gathering the data from the vehicle diagnostics. Second is to repair outcome analysis where evaluating the success of the repair. Third is the vehicle usage feedback where incorporating the user's feedback on the vehicle performance so that like you get two level inputs. Then we involve the kind of a model training where we are using a collected data to train the machine learning models. We have a model improvement enhancing the model to adapt a new pattern. We also have the stakeholder benefit where ensuring all the stakeholders get benefited from such kind of improved system. We have a remote and an automated system actions. The system can trigger the remote commands, initiate OTA updates or scheduled automated intervention, further reducing the need for workshop visit and improving the uptime. So the system identifies needs, the system detects or necessary action, trigger remote command, which include a command is sent to initiate in an action. Then we have an initiate OTA update, the system starts an over the air update. Then the scheduled automated intervention, and intervention is planned for future time. Then we have a reduced workshop visit where there is a need for a physical visit in a minimized condition. Finally, we have an improved time where the system's operational time is enhanced. Now, if you look into the role of AI in diagnostics, as far as advanced data integration and real-time analysis is concerned, it detects the subtle anomalies and pattern within the vast data set that would be difficult for human technician to identify promptly. This capability facilitates and real-time fault detection and early warning of potential failures, enabling a proactive rather than a reactive maintenance. So if you look into the predictive maintenance and fault prognostics, these AI models predict when specific vehicle components might fail by analyzing the historical and live data trends. These predictive insights help scheduled maintenance, intervention before breakdown occurs, extending vehicle life and reducing costly downtime. When we look into the fault isolation and root cause analysis, the AI-driven diagnostics employ machine learning algorithms to isolate root cause in complex automotive systems, considering cross dependencies among multiple ECUs and subsystems. This reduces misdiagnostics by distinguishing primary faults from the secondary effects, leading to more effective pairs. Now, if you look into the remote and cloud connect diagnostics, there is a kind of a collaborative diagnostic system with AI-enabled cloud-based data processing to provide a remote fault detection and a troubleshooting. It allows over the air, which you call it as an OTA software updates, and a system recalibration, minimizing the need for physical service twist. Now, when we try to look into the decision support perspective point of view, we have the natural language processing powered AI assistance, which bridges the gap between the vehicle diagnostic data and the human technician by interpreting the symptoms, suggesting the probable cause and guiding a step-by-step troubleshooting, which is considered to be a need of an hour, and based on that the systems will design. This reduces diagnostic complexity and accelerate the repair process and improving the first time fix rates. Next important point is handling a complexity and data overload in modern vehicles. With hundreds of interconnected ECUs and sensors, AI helps to manage data complexity by prioritizing alerts and synthesizing actionable insights and alleviating the technician's workload and reducing the human error. Now, if you look into the enhancing diagnostic accuracy and safety and consistency perspective point of view, the AI contributes objective analysis that minimize variability and bias inherent in human interpretation. It supports the maintenance of advanced vehicle system, including ADAS and electric powertrain, by detecting subtle issues early that they impact safety and the performance exists. So we also have a continuous learning and a system improvement where the AI algorithm evolve through the feedback from expert diagnostics and new operational data, improving diagnostics accuracy and adapting to the emerging vehicle technologies. Now, the last, which is like a role of human expert in the intelligent collaborative diagnostic system, which is considered to be one of the key aspects. Okay. So human experts, as we all know, play a critical and multifaceted role in the success and effectiveness of these intelligent collaborative diagnostic system, especially in the field of autotronics, and there is a need for a human intervention. Their involvement bridges AI capabilities and real-world vehicle knowledge and ensures accurate, reliable and context-aware diagnostics. If you look into the knowledge provision and expert judgment, the domain expert input. The experts in automotive diagnostics bring essential knowledge about the complex vehicle systems such as engine control units, ECUs, braking systems, battery management, and advanced driver assisted system. They contribute diagnostic rule, heuristic, and contextual insight vital for the system knowledge base. The contextual judgment includes experts interpret AI generated diagnostic suggestion by integrating factors like vehicle history, environmental condition, and operational context which AI may not be fully captured. Next, when we try to look into the collaborative decision making and feedback perspective point of view, validation and refinement, that's a kind of an expert review. AI diagnoses and provides an iterative feedback that helps the fine tune and improve the AI models, enabling the system to learn continuously and adapt to a new vehicle technologies. Next involves training a system where expert knowledge is encoded into rule-based or machine learning frameworks, ensuring the system evolves with growing expertise and up-to-date automotive knowledge. One of the key aspects is with reference to ethical and safety oversight. Human expert ensures diagnostic adhere to safety standards and ethical practice, particularly vital when AI outputs impact vehicle operation and passenger safety. When we look into the interpretation, communication, and trust building perspective point of view, we have a diagnostic explanation where experts interpret and communicate the reasoning behind the diagnostic conclusion to technician and stakeholders, enhancing trust and understanding of AI output. So we have a user training where experts help train automotive technician and junior engineers in reading the diagnostic data, understanding AI suggestions, and using a collaborative diagnostic platforms effectively. We have the documentation and audit trails which used for maintaining the record. Finally, the workflow integration and the system acceptance, where the usability optimization, that is, the expert contributes to designing a system interface and workflow that fits naturally into automotive service practices, ensuring diagnostic tools are user friendly and accessible. When we talk about championing adoption, they play a key role in promoting system acceptance by demonstrating benefits, identifying limitations, and providing real world insight for continuous system improvement. Now, let us talk about the real-time remote collaboration in Autotronics. So, when we try to talk about the real-time remote collaboration in Autotronics, it's a key enabled technology in intelligent collaborative diagnostic system applied to Autotronics. It allows the expert technician, engineers, and AI diagnostic engines to seamlessly connect and work together remotely to diagnose, troubleshoot, and resolve vehicle faults effectively and accurately. So we have the web-based cloud-enabled platform where we use the telematic control unit and the diagnostic trouble code unit, and this works transmitted through a cellular system, and it also has a remote diagnostic platform which provides a centralized web-based interface. In addition to this, we also have a communication and interaction tool for collaboration where it's a kind of a real-time messaging, and expert can collaborate for collaboratively annotate the diagnostic results, and it can take a kind of a, like you can take a support opinion in a very less time. Most important is with reference to the data sharing and dynamic updates, where we have a remote collaborators and the integration of the system. They come together to interact and develop the system. Then we have a decision support and workflow integration, where an AI assists by providing an automated fault detection and a predictive maintenance alert. It also takes an human expert in place. So the last is the IoT platform. So as we all are aware about IoT platform, the IoT integration which helps in the continuous health tracking and predictive analysis, especially by taking up the complement from these structures. Now, if you look into the IoT architecture, we have the business layers, the application layers, the data processing layers, the network layer and the perception layer. So in the case of a business, like it's more on business decision, application layer with reference to user friendly, and the data processing layer is with reference to network layers. So these IoT architectures are highly used for collecting the data from the vehicle sensor. Ideally, the vehicles are equipped with IoT sensors embedded in a critical component such as engines, batteries, brakes, transmissions and wires. It is integrated with the sensor and then it can be used for a complete diagnostics of the system. One of the key advantage of this IoT is the wireless data transmission to cloud platform, and another one is a cloud-based data storage and AI analytics are considered to be one of the key advantage, or I would say key features in this system. So one of like it uses a kind of a communication technologies with 4G and 5G for communication. It also uses a kind of a algorithm to make. It also leverages the collaborative decision making with respect to expert review and feedback, and it also reporting maintenance action and over the air updates. These are the benefits of the IoT enabled condition monitoring and diagnostics in autotronics, ideally towards real time data access, reduced downtime and faster diagnostics, scalability and fleet management. It has an improved experience and convenience. It has an enhanced safety and reliability. It is highly cost efficiency and maintenance optimization. It has a optimized vehicle performance. So overall, like if you look into this particular thing, we have looked into the advanced level of this diagnostics and how these structures are integrated. Now in the next class we will be taking up a component called triboelectric nanogenerator, which already we had discussed. So this has a potential application in automotive. Some of the applications of automotive we have discussed. So we will be having a lab component in the next lecture.